Here we take a look at the row method, which is the alternative to the delta method for producing the primitive forecasts that are used in the card forecasting methodology. This method is fundamentally built around an AR1, and so it differs from the delta method, which had no autoregressive dynamics. So here we begin by initializing the model. We're going to add some new indicator variables that may change values. So we have the IAR, which is going to be an indication of whether we need an autoregressive term at all. So we're going to set that equal to iRow. So that is, if we had a unit root or something that looked persistent, then we're going to assume that we need an autoregressive process. We're also going to have another one, which is iUnitRoot, which in fact will be a unit root indicator for this process, and the indicator for trend, ITR, set those equal to 0. So with those two in mind, we're going to use some of the preliminary estimators that we had. So for example, you'll see there's IR, which is our seasonal indicator. And we're going to start with this specification here. We'll actually end up re-estimating this specification a few times. We also see that we have IA, which is our indicator for seasonality. So this at the end of the day can be thought of as a seasonal autoregression with a trend and with seasonal dummies. So this is something that is a special case of the models we saw in SARIMA. Although here, we're going to make some shortcuts to simplify things. We're not going to include the extra term that often shows up in a seasonal autoregression. That is the R+1 lag. It should be M here. So it should be T minus M, which of course is the seasonal lag. So we're not going to have the M+1 lag showing up here. But that's going to be the main thing. The other thing you see is we define another set of indicator functions, which are going to be 1 in each period. So these are very simple. So we're going to have sort of M-1 seasonal dummies. And the seasonal dummies are going to only be present if we actually have seasonality for IA. So the reason to use all of these indicator functions here are just to write a sort of complete model specification that works for sort of any of the time series. Even though in practice, the model we're going to estimate for any particular time series may in fact be very simple, and we'll certainly have a much easier representation that won't include all of these dummy variables because they'll all either be 0 or 1. So we start by estimating the model, and then we're going to do what's called a unit root retest. So if IAR was 1, then we're going to do some unit root retests, in one or two scenarios. So if rho is equal to 1/2, so in other words, it's larger than 1/2, and it's plausible that the true rho may be larger than 9. In other words, rho hat plus 2 times its standard error are greater than 0.9. Then we're going to impose that rho equals 1, set unit root indicator equal to 1, and we're going to re-estimate the model with the change of YT on the left-hand side. This is how we impose that rho equals 1. So if you go back to the model on the previous page, you can see that if we set rho equal to 1 here, we then have to move this over to the left-hand side, and that will become the difference on the left-hand side. That is, we'll have delta YT, and of course we won't have the rho YT minus 1 term there anymore because we'll have imposed that rho equals 1. On the other hand, if you estimate this model and end up with a negative estimate of rho hat, then one would set IAR equal to 0 and re-estimate the model. Of course, if we set IAR equal to 0, you can see that if we put this equal to 0, then you wouldn't have any autoregressive terms at all in the model. So you can think of this as sort of doing a model selection process in a very simple and easy to automate fashion. Next, we're going to revisit it. We're going to implement a trend test. So in the case if we didn't have a unit root before, so only in the case we don't have a unit root, then we're going to test whether the series is stationary, whether the series requires a trend. We're only going to do this if t minus k is greater than 10, where k is the number of parameters in the most recently estimated model. And we're going to test whether the cumulated residuals have mean 0 using a t-test with size 1. If the null is rejected, then we'll assume we have a trend. By cumulative residuals, what we're going to do is we're going to split our sample in half, and we're going to think of our epsilon hats t, so we think of the sum, t equals 1 to cap t over 2, divide that by 1 over t over 2. We're also going to have the sum t equals t over 2 plus 1 to cap t of epsilon hat t. Again, divide that by 1 over t minus 2. Then we're simply going to use a t-test difference of these two to test whether the two are actually the same. So at the end of the day, you could think of this as epsilon bar 1 minus epsilon bar 2. We make a simplifying assumption here that their IID, so the variance of the sum, is the average of the variances. So each of these series here, the variance of each one is going to be sigma squared divided by t over 4. We have two of them, and we again assume they're independent, so the variance of each is sigma squared over t over 4. So then the variance of the sum is simply going to be sigma squared over t over 2. So in other words, we then divide this by the square root of sigma squared divided by t over 2, which then can finally be written as t over 2 times epsilon bar 1 minus epsilon bar 2 divided by sigma. So in other words, if this number is large, then we're going to assume we need a trend. If this number is small, then we'll assume we don't need a trend. Intuitively, if you have a trend in the series that you've neglected, so you have a strong time trend, of course, with a constant, we know residuals be exactly mean 0, but what you'd find is you'd have more negative residuals before the midpoint of the series and more positive residuals after the midpoint of the series. So if we do find evidence of a trend at 1% using this simple t-test method, then we'll set I trend equals 1, and of course every time we change a model parameter, we re-estimate the model to get the latest version. We're then going to do an additional trend check if we found a trend in the previous step, and if we find that adding the trend gives us a very large negative AR coefficient, so if rho hat is less than -1/2, then in fact we'll remove the trend and re-estimate the model. This happens if the trend and the AR are competing against each other heavily, or if the sample size is small, one might see this. And so it's just a step to make sure we haven't over-specified the model. Moving on, if at this point, if indicator unit root is 0, then we actually have our final version of the model, and we produce forecasts just like it's any seasonal autoregressive model, possibly with seasonal dummies and a trend. But there's, at this point, it's just a totally standard model, a special case of the stream of models we talked about in the earlier slides. If, on the other hand, IUR is 1, then we're going to use one robustness method. In particular, the trend is going to be damped, such that you're going to take the max, if the trend is positive, you're going to take the max of 0 and the trend estimate that we actually have in the data, minus S, where S is this particular number here. So this is to give it as a sort of critical value that depends on the residual variance and obviously the sample size. If, on the other hand, the sort of trend estimate is negative, then again, we say the trend, but in this case, it's mu, which is this first coefficient. But again, we're in the IUR case, which is delta YT is on the left-hand side. So this really is the trend, or in fact, we really should think of as mu hat as the drift. So we're going to robustify the trend by changing the drift, and we're going to basically shrink the drift towards 0, possibly set it to 0 if it's very close to 0 in a sort of statistical sense. If it's far from 0, then we'll still shrink it towards 0 a little bit. And this is the idea of robustifying the trend. But once I've changed that parameter, I just forecast with the model as if every other parameter is the same. So the rho method adds a seasonal AR component with seasonal dummies and possibly a trend as an alternative way to forecast from delta. It uses a sequential procedure to select, a simple but reasonable time series model for the data, and it imposes sometimes a modest amount of robustness when forecasting the trend, at least when we have a unit root.